Hello, and welcome to Cooking with Chemistry. I'm your host, Chef Matthew Google, and today we'll be cooking Crema Catalana, a delicious Spanish custard dessert. To cook, you'll need 1 1/2 cup of heavy cream, 1/4 cup of sugar, 1 1/2 teaspoon of vanilla paste, or in this case we're going to be using scraped vanilla beans, a few strips of lemon zest, we'll be using 5 egg yolks, and an excess of sugar for caramelization. Now, with ingredients out of the way, let's get cooking. First, in the background, preheat an oven to 325 degrees Fahrenheit with a rack in the middle. Let's also prepare our ingredients. We can start by peeling a lemon with a peeling tool to get our lemon strips. We're going to cut about 5 or 6 lemon strips for this recipe. Now, we'll prepare the eggs. Crack them on the side of a large bowl and dispose of the egg whites, keeping only the yolks. You can save or store the whites if you'd like, so that you can use them for other recipes or to make eggs in the morning. We'll return to the eggs in just a moment. For now, though, grab a separate, smaller bowl and pour the heavy cream. Then, add the vanilla paste or extract. If you're working with a bean like we're going to be using, slice the bean lengthwise and gently scrape out the insides. Add this to the bowl, and then lastly add the 1/4 cup of sugar as well as the lemon zest, and mix well. After mixing, pour into a saucepan and cook on medium-low heat, stirring every now and then to avoid burning the mixture. Cook until the mixture comes to a gentle simmer. At this point, the cooking of the mixture works to better combine its contents. However, it also facilitates the neutralization of the mixture's pH. Lemon juice is naturally highly acidic with a pH between 2 and 3. Lemon zest also takes on similar properties, so adding it to the mixture decreases the overall mixture's pH. Since the rest of the ingredients have generally neutral pH levels, or about 7, adding an acidic ingredient thus lowers the pH. This change in the acid-base equilibrium gives our sought-after slight sharp and tart flavor. Let's return to the eggs. As the mixture cooks, whisk the eggs together until thoroughly beaten and combined. You should notice they become frothy and turn a slightly lighter shade of yellow. This is what we're looking for. And you can stop if you wish. Once your main mixture has cooked to a simmer, slowly begin to pour about 1/2 cup of the heated mixture into the bowl of egg yolks, making sure to stir the yolks constantly as you do so. Once incorporated, slowly stir in another 1/2 cup. The outside of the bowl should feel warm, indicating the yolks are being heated. Finally, slowly incorporate the rest of the cream, continuing to whisk constantly. Smells so good. Smells so good. Now thoroughly combined, filter the mixture through a fine mesh strainer into a measuring bowl for distribution into small ramekin cups. This recipe calls for a second phase of cooking, this time in the oven. For the second cooking period, we are going to steam our mixture in separate ramekin cups to create the desired gelatinous consistency, and even cook the custards throughout. To prepare your ramekin cups, place them evenly spaced in a large roasting dish or brownie pan, Anything with edges as high as the ramekin's sides will do. Then, evenly distribute the custard mixture among the cups. We found that pouring a little over halfway into each ramekin worked best for us, but feel free to experiment with using different volumes in each cup to produce different final results. After distributing the mixture, cut a piece of foil to cover the cups and wrap over the edges of the pan. In order to allow the system to vent steam and regulate itself while cooking in the oven, cut a few holes in the foil where the ramekins are not underneath. This would allow steam to escape. Now we wait for the oven to finish preheating. Once your oven has reached 325 degrees Fahrenheit and is ready, pull out the middle oven rack and place the covered dish on it. Gently lifting back the foil on top, carefully pour enough hot tap water into the pan so that the water level reaches a little more than halfway on the sides of the ramekins. After adding the water, reseal the foil on top, push the rack and pan back into the oven, and let it cook for 35 minutes to start.
Ready?
Yep. While this is cooking, let's discuss more of the chemistry behind what's going on here in this dish. Now, any chemical reaction can be examined based on a principle called Gibbs free energy, the value of which determines whether a reaction or our mixture we're cooking will take place or not. The equation to find Gibbs free energy goes as follows: delta G equals delta H minus T times delta S. Now, this may sound like a mouthful, but let's break it down piece by piece and see what's going on here. Delta G represents the actual value of Gibbs free energy, and the sign of which, positive or negative, will tell us whether or not our mixture will cook into our desired custard. Next, delta H represents enthalpy, or the change in heat of the reaction. If the enthalpy is positive, then the reaction is endothermic and requires heat to be put into the system in order to undergo the cooking reaction. The positive value thus symbolizes an increase in the local system's energy, the local system being the cups of mixture. If the enthalpy is negative, then the reaction is exothermic and will begin without the need for excessive heat, instead releasing heat into the surrounding environment. The negative value in this case represents a decrease in the local system's total energy. Since we're constantly adding heat to our mixture both on a stove burner and in the oven, it's safe to say that our reaction is endothermic, requiring heat to be put in. Thus, our delta H is positive. T represents the temperature of the system, recorded in Kelvin. Depending on the reaction's delta H and delta S values, the overall reaction may behave differently depending on what temperature it's at. For most of the cooking process, our mixture's temperature is at 325 degrees Fahrenheit, or about 436 Kelvin. Finally, delta S represents entropy, or the change in randomness during a reaction. Naturally, the world tends to move towards disorder when possible, often having a positive delta S, which shows an increase in randomness. However, some reactions do tend towards creating a more ordered product, instead having a negative delta S due to the decrease in randomness. Since our mixture is breaking down into a greater number of smaller particles to release flavor, we can assume the cooking of our mixture has a positive delta S. That is, the reaction during cooking produces more randomness through producing more individual particles. Altogether, we get a free energy equation with a positive delta H and positive delta S, meaning we will only have a negative delta G at higher temperatures. To explain this, let's make up some numbers. Let's say the delta H, or enthalpy of our mixture, cooking, is 400 kilojoules per mole, and the delta S, or entropy, is 1 kilojoule per mole. Plugging these positive values in at room temperature, or about 298 Kelvin, the delta G, or free energy, would be about a positive 102. The positive value at room temperature means this reaction is not thermodynamically favorable at room temperature, and therefore wouldn't occur, being called non-spontaneous. However, at a higher temperature, like that of our oven, at about 436 Kelvin, the free energy would be about a negative 36. The reaction would then be spontaneous at this higher temperature because of the negative delta G. Overall, we can deduce that because of the positive delta H and delta S, our delta G will only be negative, and thus our reaction thermodynamically favorable or spontaneous at the higher temperatures provided by an oven. Phew, that was a lot. Let's take a moment to check back in on how our custards are doing after 35 minutes in the oven. To check, pull out the oven rack and gently pull back one edge of foil to reveal a ramekin. Proceed to gently jiggle the cup. We are looking for the custard to have a somewhat liquidy appearing center with more set edges. This hasn't occurred yet for us after 35 minutes, so put the foiled pan back in for another 5 minutes. Repeat this process until the desired consistency is met. Don't worry if your custard hasn't fully cooked after 30 minutes either. The reactions occurring during the cooking of the custard evolve slowly and often take longer than the recommended 35 minutes. Since the rate constant K of reaction is directly related to the length of time reactants in reaction take to form into products, the slow speed of cooking indicates the custard has a low rate constant K, causing it to take a longer amount of time to cook. For this batch, it took about 15 extra minutes, but your results may vary. Once thoroughly cooked, remove the pan from the oven and let cool to room temperature. Then, remove the custard ramekins and cover with plastic wrap. Place these in the fridge to finish setting for at least 4 hours. We let the custard cool for such a long time in order to facilitate a phase change and condensing period. Immediately after removing from the oven, at the particle level, custard particles have a lot of kinetic energy and are in a liquid state of matter, freely moving past each other. When in the fridge, the custard particles transfer much of their kinetic energy to the colder air surrounding them, thus becoming slower. As their kinetic energy continues to decrease, the impact of the pull of intermolecular forces, like London dispersion forces, caused by the natural wobble of particles' electron fields, increases, making the particles move past each other less freely and eventually settle into a condensed matrix, also known as the state of solid phase. The solid state of the custard is even more gelatinous than when it's a liquid, which is why we let it cool for so long to achieve this state. Finally, after the custard is set, sprinkle a thin layer of sugar in an even coating across the top. Then, using a kitchen torch, heat the sugar in circular motions, making sure the flame just barely touches the surface of the custard. The sugar will bead up and turn a deep golden brown as the carbohydrates within are oxidized to create a classic caramelization reaction, releasing delicious flavor and sweet scents. This reaction is also thermodynamically favorable at higher temperatures, requiring energy to be put in. However, unlike the cooking of the custard, the caramelization occurs relatively quickly, revealing the reaction has a larger rate constant K than that of the custard. Once most of the sugar is caramelized, let the dessert sit for a minute or two to return to room temperature. After that, the custard is complete. At this point, feel free to add any complementary fruits on top, and then dig in. So as you can see, it's hardened up by now. we push through and just break it up a little bit, comes a little messy. You can push through, get that nice gelatinous, very good Crema Catalana consistency. Let's take a bite here. Pretty good. Pretty good. Delicious.
Move your spoon. Do you want to take one more spoonful?
Sure.
Can you taste
Very good.
the lemon and the vanilla?
Oh yeah, you can definitely taste the nice acidicness of the lemon and the sweetness that comes from the vanilla, as well as the very sugary top, which has a nice crunch.
Because we infused those flavors while they were cooking on the stove.
Exactly.
In the cream.
Congratulations! You've just learned how to make the delicious Crema Catalana and learned some of the fascinating chemistry behind it. I hope to see you again soon next time on Cooking with Chemistry. Peace.